Good afternoon, Novi, Michigan. Greetings from Sweden and all of us here at China Euro Vehicle Technology, where we create mobility solutions for a different tomorrow. My name is Vijay Ramnath, and this is my colleague Adam Brandt. Now, China Euro Vehicle Technology was started about 10 years ago in the west coast of Sweden in Gothenburg. Now, we are the R&D and innovation center for Zeekr in Europe, and our clientele includes Volvo Cars, Lotus, Polestar, and Lynk & Co. We are about 1,500 researchers, designers, and engineers, and we are asked to think big, find a way, and inspire day in and day out. As some of you might have already guessed, we are part of the Geely Group. And apart from the brands I mentioned previously, we also have Geometry, Proton, Chow Chow Mobility, and LEVC, the makers of the iconic London taxi. Our technology solutions include over 2 million deliveries of the CMA platform, the award-winning 7DCT hybrid transmission, the pioneering Lynk & Co app, one of the first customer-to-customer car-sharing app, where the phone is used as a key. And more recently, our collaboration with Waymo has been instrumental in giving us a strong foundation in highly automated vehicles. Now, the SEAM platform is ideal for self-driver system integration. With its vast interior, a comfortable ride, and B-pillarless design, we are putting the rider at the forefront. Now, for any of you visiting Europe in the coming weeks, I would strongly urge you to experience the Zeekr 001 and Zeekr X, who are getting ready to roll in Europe very soon. Now, we've had the DiM250 at CEVT for about 2 years now, and in no way has it been a one-dimensional tool. It was quite natural for the vehicle dynamics department to drive the activities and take the lead. So we started with some base chassis where we could implement chassis real-time tuning. We're also able to set up model exchange methods with our suppliers. For example, we exchanged models with steering suppliers, and not just the model, we also got the steering field tuning interface. So what that did was give us a great intuitive insight into all the parameters and the consequences of changing these parameters. So even though we were on the left side of the V cycle early in the project, the maturity level of our engineers was quite high. We also used the active brakes to define brake-by-wire maps. So with brake-by-wire systems, you can decouple the brake pedal system and the hydraulic system. And that gives you freedom to separately define these maps for the pedal feel and also the pressure deceleration. Now, it's not so easy to do this when you are developing a new platform. And we were able to have multiple workshops with our brake engineers, and they were able to communicate a baseline map and also future requirements and areas of improvement to our supplier. We also evaluated cross-functional aerodynamic and vehicle dynamics, which my colleague Adam will talk a bit more later. And we were at a crossroads at this point. Should we do more ride comfort studies, maybe more complex tire models, or should we perhaps try to push the usage of the tool across the company? So we extended the usage and implementations to HMI and ADAS, which I will cover a bit more, but also motion control. Now, the benefit of having a simulator is that you are not architecturally constrained. So you can ask yourself big picture questions. And I would like to cover 2 topics here. One is the rear wheel steering and steer-by-wire third actuator. Now, with steer-by-wire third actuator, you have to think of redundancy. So what happens when the primary mechanism fails and also your backup mode fails? How do you bring the vehicle into a fairly safe position? Should I maybe use the brakes and powertrain, which mainly control longitudinal direction, to perform a lateral minimum risk maneuver to the side of the road? Or should we maybe have a rear wheel steering in the vehicle as a natural redundancy? Now, the studies and experiments we did in the simulator correlated really well with the suspension parameter changes and also the brake pressures that the suppliers were proposing. And mind you, the suppliers have been working a lot for many years with physical prototypes. And this was very good positive reinforcement for us that the simulator is the right tool to accelerate our function development. Now, the rear wheel steer in the DiM250 is a particularly special implementation because it was one of our very first. Our product managers were interested in understanding the effect of rear wheel steering in a mobility-based vehicle. So think low speeds and tight turning corners in cities. Now, what we were able to do was implement an actuator in the rear axle in Adam's car. And of course, we did the usual KNC loops and also the turning circle evaluations. And then we translated this into car real time. And parallelly, we developed a controller in 2 stages. One, a very simple controller, which worked out of phase at low speeds and in phase at high speeds. But also we extended the complexity to a yaw rate-based feedback controller. Now, mind you, we still kept this fairly generic and tunable and simplistic. Now, apart from positive internal stakeholder feedback regarding the agility benefits of the vehicle, we also were able to connect this controller to an external customer whose model was completely hidden and obfuscated. And we invited them over to test drive their model with our controller. And we got really positive feedback that the changes in the parameters reflected a rear wheel steer vehicle in reality. And they were able to adjust parameters like virtual wheelbase versus vehicle speed, for example, and get a really subjective feel for it. The DiM250 also has helped us take the first steps into ADAS. Now, here is a demonstration of the evasive maneuver assist function. Now, when you are beyond the point of autonomous emergency braking and you initiate an avoidance maneuver, this function, which you will get a closer look at now, helps you come back into the lane. Now, you can do this in multiple ways. You can do it either with just a steering assist, or you could combine a steer assist with some individual wheel braking. And we were able to run sessions with our colleagues and understand the aggressiveness of these steering assists. And this was really an invaluable exercise. So I will now hand over to Adam, who will take us into the fascinating world of aerodynamics. So Adam.
Yes, thank you, Vijay. So I will give a short presentation of how I use the driving simulator in my PhD work, where the project was focused on high-speed driving stability, coupling both aerodynamics and vehicle dynamics. So first, a brief introduction to driving stability. What is driving stability? And the scenario that I focused on in my work is what we can see here. So we are driving on a straight road and we drive above 100 kilometers per hour, so above roughly 60 miles per hour. And there is no maneuvering, just try to keep a straight path on this highway. And if you have issues with driving stability, this often comes as some sort of vehicle nervousness, and that you need to do these small corrections with the steering wheel to maintain this straight path. This, of course, causes discomfort for the passengers and for the driver, and it's not a very premium feel of vehicle if you need to do these corrections to maintain the path. So, of course, automotive manufacturers want to avoid these stability issues at any cost. Furthermore, I divided driving stability in my project. I divided it in 2 different subtopics, namely crosswind sensitivity and high-speed stability. And I used the driving simulator for both of these different subtopics. And I want to just briefly introduce the differences between the 2. Crosswind sensitivity, that is an external effect, and typically that would be a gust hitting the vehicle. For example, when you go up on a bridge in crosswind conditions, you get this sudden crosswind affecting the vehicle. And in aerodynamics, we mostly look at lateral aerodynamics, at side force and yaw moment. For high-speed stability, on the other hand, this is more of a self-induced stability effect. So depending on how you design the exterior of the vehicle, you can get some fluid dynamic effects that cause these stability issues, this nervousness of the vehicle. And here it's mostly vertical aerodynamics. Furthermore, driving stability is usually evaluated quite late when we are developing a vehicle. And this can cause some problems, since at this late stage it's quite expensive and difficult to do improvements to the vehicle. But this is usually how it's done. We start with going to the test tracks when we have the prototypes. But we want to move from this road testing towards more lab testing, using, for example, a wind tunnel, or in this case, a driving simulator, to be able to do this work much earlier in the development phase. And further on, we can move on into the virtual environment where we can do CE simulations. So for my work in the driving simulator, I developed aerodynamic models that I coupled using Simulink, coupled it to Vijay Car Real-Time that could run on the simulator. So then we could experience different crosswind gusts and different high-speed stability load fluctuations from the aerodynamics. And I will briefly go through the methodologies in these two different studies, starting with crosswind sensitivity. I evaluated two different gust profiles. Profile 1 that has the gust shifting from one direction to the other, that can cause issues for the driver, and then profile 3, which is more of a step function from one direction. And I also implemented a two-way road perpendicular coupling. So the gust is always described perpendicular to the road, but we can have motions of the vehicle. So we have this two-way coupling between the two disciplines. So with this, we can, with the position and the velocity of the vehicle, we can calculate the relative flow velocity affecting the vehicle and the relative flow angle of attack affecting the vehicle. And these two can be fed into the aerodynamic models that approximate the aerodynamic gust forces. Furthermore, it's been seen that most crosswind gusts occur from driving into different wind conditions, not these local variations in time that we can experience when we walk outside. But since we drive at so high speeds, it's more common that we drive into new conditions. And a typical example would be when we go up on a bridge in crosswind conditions, we go into the new conditions. So based on this, I can show you how we developed a coupling methodology. So on the y-axis, we can see the crosswind velocity, and on the x-axis, we have the driving distance of the vehicle. So you can see this is profile 1 described here. This is the vehicle drawn to scale, but to prove my point, I enlarged the vehicle. So as we drive along the road, at some point, the front of the vehicle will be affected by this crosswind gust. And then we have a small time delay until the same conditions occur at the rear of the vehicle. So with this small time delay, we could formulate a aerodynamic model. We call it the aerodynamic QSD model. It's a quasi-steady model that accounts for this axle delay. And if you want to read more about the model, it's published in Vehicle System Dynamics. But basically, we take the aerodynamic forces and we split them up into front and rear axle forces, adding the time delay and merging them back together. So with this methodology for the crosswind, we can evaluate different gust profile. We can see when the test drivers experience stability issues due to strong gusts. And we can also find out how we can design a vehicle to be less sensitive, both in terms of aerodynamic parameters, but also vehicle dynamic setting. So moving into the other topic of high-speed stability. And here it's more of these self-induced stability effects that I talked about, depending on mostly on the wake dynamics, the air behind the vehicle. So for this, I used scale resolving CEVT simulations, and these are quite accurate aerodynamic simulations in time, but they are very, very expensive to run. So in this example, I simulated 5 seconds of physical time, and it takes 10 days to run one of these simulations on a high-performance computing cluster. And what we evaluated was here you can see some unsteady flow fields behind the vehicle, as you can see. And what I evaluated was two different roof spoiler designs. We have this baseline spoiler in blue. And when we have this spoiler on the vehicle and take it to the test tracks, we can experience in this nervousness and these high-speed stability issues. And we also have a version that solves the stability issues. We call it the improved spoiler. Unfortunately, this improved spoiler has higher drag than the baseline spoiler. So that is what we want to understand. Why do we get stability effects for this baseline spoiler? So if I plot the rear lift coefficient here, you can see first of all that the improved spoiler has on average a lower rear lift coefficient, the average value, compared to the baseline spoiler. But what I will argue for, and what I argued for in my thesis, is that this is not the cause of the improved stability. It is because we have these low frequency fluctuations for the baseline spoiler that we do not have on the improved spoiler. So I used the driving simulators to prove this point. And how did we do that? We see that we have only 5 seconds of physical time. So I duplicated this data and merged it together to form a 2 to 3 minute long recording of the forces that we could sit in and experience in the driving simulator. And for this, we had 3 professional test drivers that usually do these kind of evaluations on the test track. So if we move into results, I will present them using this graph. So on the x-axis, we have the rear lift fluctuation scaling. So scaling into 1 would be the fluctuations that we had from the CEVT simulations. And on the y-axis, we have the rear lift coefficient adjustment. So as we move down here, this means that we increase the downforce on the rear axle of the vehicle. And according to theory, when we increase the downforce, at some point we will have a good stability performance of the vehicle, which was also the case when we did the blind testing in driving simulator. You can see that, but we can see that we need quite high downforce values to be able to make this vehicle stable, to have a good stability performance. On the other hand, we can also move on the other axis, and we can see that we can keep the same average value of the baseline spoiler, but if we manage to reduce the fluctuations, we can also create a stable vehicle. I also did some combinations to fill in this design space. And we can also present the improved spoiler in this graph, where you can see that we have slightly lower average value, but most of all, we have reduced the fluctuations using this spoiler. So with this, we can see that we have 2 different regions of bad stability performance and better stability performance, and we can form a diagonal line here where we can see that both of these quantities are affecting the stability performance. I want to keep on the left side of this diagonal line. And I also did some analysis of the linear bicycle model, the classical bicycle model. And driving at 180 kilometers an hour, I wanted to investigate what happens if we increase the rear axle lift force. And what I found was that when we increase it enough, we get real positive eigenvalues of this linear system, meaning that we have a mathematically unstable system. This is not any point we reach where we get mathematical instability of a vehicle. But here we can see where this point lies, quite high lift values, but it agrees quite well with this diagonal line. So conclusions. We see that both the driving simulator can be used to assess both crosswind sensitivity and high-speed stability. And as I just showed you, we found that the aerodynamic lift force fluctuations greatly influence the high-speed stability performance. The aerodynamic properties and loads can also be altered while driving, enabling back-to-back comparisons and also investigations on active aerodynamics. We could switch between the baseline and the improved spoiler while driving to compare them back-to-back. This is a great advantage of the driving simulator compared to doing it on the road. And finally, we think that for an electric and autonomous future, we need to comprehend the cross-functional sensitivity of the design choices, and we think that the DiM250 is an ideal tool to provide this needed holistic understanding of a vehicle in early development. So thank you very much for listening to our presentation.